Let's see why RSA works. So why is it that doing the RSA operations, you're actually able to decrypt the message? So let's recall the setup essentially. So you had your two primes, P and Q, that Bob knows. Bob then computes this n. He computes phi of n using P and Q, so he can do this. And then he selected an E, and he then computed the inverse of E mod phi of n to find this D here. And so E times D is congruent to 1. And the idea was that, let me write it here then. So the public key was N and E, and the secret key was N and D. And then how did it work? Well, if Alice wanted to encrypt a message, she would just take it to the power of E mod N and send it. And then how does Bob decrypt? Whatever he receives, he takes it to the power of D mod N, and it should give you the original message. So essentially what we need to show is that this is true. So that if m to the power of e to the power of d is congruent to m mod n, then we show that you're able to decode essentially. So let's do this. Let's break it into cases. So suppose first that the message and n are coprime. So they have GCD1. So in that case, if that happens, then by Euler's theorem, we have, so Euler's theorem tells us that m to the phi n is congruent to 1 mod n. So go see the video on that again. So Euler's theorem tells us that m to the phi n is congruent to 1 whenever GCD of m and n is equal to 1. So we have this result. So now, since ED is congruent to 1 mod phi n, so what does this mean? So this means that ED, when you divide it by phi n, has a remainder of 1. So in other words, ED is equal to 1 plus something times phi of n, right? So if you divide ED by phi of n, you get, it's going to be k times phi n plus 1, because this is the remainder that you get when you divide by phi n. Okay, so this is for some k integer, right? Thus, so since this is true, now we can compute. So if we do m to the e to the d, right, which is just m to the ed, of course. So this is going to be equal to m to the 1 plus k phi n. Let's make all congruences here. 1 plus k to the times phi n. And so this you can rewrite it as m times m to the phi n to the k. So this is just rewriting. So the plus 1 you just multiply by m, and then k fn you just write it like this to the power. Now we know that m to the phi n is congruent to 1. So in other words, this is just m times 1 to the k, and 1 to the power k is just 1. So this means that this is just congruent to m mod n, which is what we wanted to show. So with this, we showed that if Alice is sending any message where the GCD with n is 1, so any message that is coprime with n, it will decode correctly. So Bob will be able to decode by just taking the df power of whatever he received. But let's show that this will be true even when this doesn't happen. So now let's look at the other case. So suppose now that they are not co-prime. Suppose that the GCD of M and N are not 1. Now what does that mean? Now that means that at least one of the prime factors, P or Q, must divide M. So remember that N is equal to P times Q. This is the factorization of N. So if they share a common divisor, it needs to be either P or Q. Like at least one of them has to be there. I mean, it could be both, but at least one of them has to be there. So let's separate in cases here. So let's suppose, so if P divides M, let's see what happens. So if P divides M, then of course you get what you want. Why? Because M to the ED, so if P divides M, then M is just congruent to 0. And so if M is congruent to 0, then 0 to the power of anything is 0, and that's it, right? So mod P. So in other words, if P divides M, it doesn't matter what you do with the message, you're just going to get 0 here. And that it will be the case that M to the ED is actually congruent to your message. Now, if P does not divide M, right, then M is relatively prime to P. And so what this means is that we can use Fermat's little theorem. So go see that video again. So by Fermat's little theorem, we're going to have that M to the P minus 1 is going to be congruent to 1 mod P. Now, remember that E times D, so we saw E times D is congruent to 1 mod phi of N. So E times D is congruent to 1 mod phi of N, right? And so since, and wait, okay, so we saw that. Now, since phi of N is equal to P minus 1, Q minus 1, this also means that ED has to be congruent to 1 mod P minus 1. And so what this means is that for some integer, so then ED is equal to 1 plus, let's say, R times P minus 1 for some integer R. So yeah, so for some integer R. And now we can just rewrite then M ED. So this, we can just rewrite it as 1 plus R P minus 1, which will be congruent here to M to the P minus 1 to the R. And we saw M to the P minus 1 is 1, so this is just going to be congruent to M mod P. Which is what we wanted to show. So that means that in both cases, so if P divides M and if P doesn't divide M, so those are all the possible cases. So in both cases, it's always true, it's always going to be true that M to the ED is congruent to M mod P. Now you can do the same argument to show that the same is true for Q. So N is equal to P times Q, and we're saying if P divides M, this happens. If P doesn't divide M, this happens. If you just replace Q here, if you replace P for Q, and you rewrite everything, and you replace P for Q here, and you rewrite everything, you actually get the same exact statement mod Q. And so we have these two. So it's true that these both are true. But guess what? You can now apply the Chinese Remainder Theorem. So now, from the Chinese Remainder Theorem, and go watch that video again, that means that this is true mod P, this is true mod Q, and P and Q are coprime, so this will be true mod P times Q, which is N. So this will imply MED congruent to M mod N. And so this will be true always. And this is what we wanted to show. So this is why it's always the case that you can decode RSA. This is why RSA works. And you can see that we used sort of all the main results we showed in the course. So you're going to have to go and check Euler's theorem. You need to go and check Fermat's theorem. You need to do Chinese Remainder Theorem. This uses everything we've seen, right? And uses all the modular arithmetic. So this uses all the tricks we've learned in this course. So yeah, so this is why RSA works.